So now we're going to move on to part B. So part B really means that to show that the ring R is commutative. In other words, what we need to prove or to show is that for all A and B elements in the ring R, we need to show that, let's see, we want to show that commutative, meaning that A times B is equal to B times A. And of course, again, it is for all A and B in the ring. So keep that in mind. Commutativity is not something that is always given when we're in high-level algebra. So, for instance, if we think of matrix, such as a matrix looks like this, and then we have a matrix like this, okay? If we try to multiply it this way, we'll actually end up with a different result as if we try to switch the order and multiply together, okay? Now, again, these two are not the same. That's saying that for some kind of rings, we will not actually get A times B is equal to B times A for some particular A and B. So how are we supposed to prove it? Well, since we already proved that for any elements in this ring here, two copies of the elements adding together is actually equal to 0. We might as well just try to use that. So how do we set up? We can actually set up in the following way. We're going to start off with A plus AB plus AB plus B. Now you may ask where this part comes from, but as we follow the proof, you'll be able to see why we actually will start with this. So from part A, we already proved that if we have two copies of elements in this ring adding together, these two will be cancelled out. In other words, in this case, we have the AB plus the AB is actually equal to 0 here. Therefore, if this cancelled out, we just end up with A plus B. And of course, A plus B is also the same as A squared plus B squared. So in other words, at the beginning, we also actually started off with A squared plus AB plus AB plus B squared. Now, keep that in mind again. Here we can already factor out. This is the reason why. We're going to continue the proof and see how this is going to change. Because A and B are both elements in the ring, the sum of these two, meaning the A plus B, is of course also an element in this ring R. And therefore, using the condition for all elements in this ring, the square is actually equal to the element itself. We can actually square out this particular element, A plus B. In other words, we can just rewrite this as A plus B times A plus B. Now, we just need to FOIL it out. So we have the first term, A times A. And again, A times A in this case, as a ring, we will actually get A squared. And then now, for foiling, we have the outer part, A times B. So in this case, we have A times B or AB. Next, we have the inner part, B times A. And here is the reason why we cannot really rewrite this after having A squared and B squared. We cannot just rewrite it as the square of something, because we did not prove that this ring is commutative yet. In other words, we cannot guarantee that B times A or BA is in fact equal to AB. And this is actually what we need to prove. Okay? So again, I'm going to color code it. For the green part, we have A times B giving us AB, where the red part is B times A giving us BA. And after that, of course, we have the last term, B times B, or again, B squared. Then what should we do next? Well, using our condition that the square of an element is equal to the element itself in this particular ring, since A is actually an element and A squared is of course the element in this ring. So we can rewrite that A squared is equal to A, and then for our last term, B squared is actually equal to B. Thus, we now have A plus AB plus BA plus B on the right hand side. Finally, now we can cancel out the A and the B on the left hand side, because for any ring, we already have addition being commutative. So we can in fact try to rearrange the order. Also, we know that for the addition part, if we just try to take a look without the modification, the addition part is already forming a abelian group. Therefore, we already have the parts that we have the additive inverse for all elements, and we can actually do the inverse of addition, or what you guys call subtraction here. And therefore, we can actually subtract A on both sides, as well as subtracting the B on both sides. And now we also have the AB term on the left-hand side of the equation and an AB term on the right-hand side of the equation. Thus, we can also try to cross this out, such that at the end, we end up with only the A times B on the left-hand side and the B times A on the right-hand side of the equation. And because this holds true for all A and B in this ring, it actually shows that the ring R is in fact commutative. Before we move on to part C, I would like to show you guys the wrong way of proving part B. So there are actually two wrong examples that are coming up of how to prove part B. Okay, and after that we'll continue and finish part C.